Okay, now we'll get into Unit 6, second part, ceramics. So in this part, we're going to take a look at the properties of ceramics, especially mechanical properties. So the properties of ceramics are they're just a function of composition, okay, and structure. Again, the properties, they depend highly on the structure of that material and the composition of that material. And those are the reasons why we change them. Okay, we change the composition, we change the structure, and we see what happened to the properties, and then we're going to select the properties that we want to use and apply it in all the things that we want to do, okay, with that material. So it's pretty simple, but a lot of work in it, and you can do it alone. Many different groups do many different things, and then pass it to the next generation, and we carry on, yeah. Ceramics are again hard, brittle, so they do not deform plastically, okay? Also, they do not conduct heat or electricity readily. They can conduct heat or electricity, it's not going so fast, okay? It's gotta go little by little. For metal, it goes like really fast. For ceramic, it takes time. This is showing the ceramics and your plastic polymer here. Polymer is even difficult. So mechanical properties, we would take a look at tensile strength, compressive strength, your flexural strength, stiffness, and fractural toughness, and hardness. Okay, these are all the properties we'll take a look at in this unit. Ceramic is composed of various sized particles, so when they fuse together, there are voids and small cracks produced inside of the ceramic body. So ceramics in tension or under tension, you're going to see these voids are their weaknesses, and failure usually happened at these places, okay, where the voids are. In compression, these voids they have tendency to fuse together, and by doing so they resist failing, and that's happen only in compression. For tension, failure will happen because of these voids, okay? Ceramics, they have been used for applications where resistance to compressive forces are required. So compressive strength in ceramic is many times greater than the tensile strength, okay? So some students may have difficulty if you're not engineering student or don't have a lot of engineering background or science background. Try to understand compression like these arrows, okay? The force is gonna go inward. The tension is kind of like that, okay? When the material is applied, some sort of stress or load, okay? Compression going in, tension coming out. And that strength for this material is greater than that strength for the same material. Yeah? Meaning that they will compress more than they go into tension. So it's very possible to achieve high tensile strength. So we can go from 0.7 mega psi to 1.4 mega psi in newly drawn glass fiber. Glass again is a ceramic glass. When we say fiber, we're talking about them at the molecular level. M, a big M is you have 60, okay? So you're looking this 10 to the power 6 for M. So in practice, if you have like a very small flow in glass fiber, it's gonna definitely dramatically decrease that tensile strength, even if you can go so high. One single floor can mess up everything, okay? So that's why, therefore you have to be very, very careful. I'm gonna go ahead and erase this. Then we can test the tensile strength of ceramics, but the testing is difficult and also expensive. And we call tensile testing in ceramics. Those tests are called Flexural tests. So all information related to tension of ceramics is achieved through Flexural tests. Okay, so Flexural test is performed this way. So you're gonna have a beam of your sample, a standard size. It has to be a standard size because if you want to compare the tensile strength of different ceramic types, then you definitely need to have a reference, and we usually make the reference as a standard size, okay? So you're gonna place that beam between 2 points, and then we're gonna apply the force perpendicular to the beam. So that force the beam is going to experience is going to be on its lower surface. So here you can see your beam is right there, and the force is applied with this machine perpendicular to the axis of that beam. So the beam is going to experience the tension forces on its lower surface. Okay. Don't forget that. So flexural strength, we are going to calculate it by using this formula. MOR is modulus of rupture, and that is for the flexural strength. We're gonna apply the force, the perpendicular force, and then your beam length, that's the ceramic length, ceramic beam, okay, standard size length. You're gonna times with 3 divided by the width of the test specimen is your B, meaning like the width of that beam, okay, and then your height. So your L, your W for width, and then your height H of the specimen, and square your height, okay, times 2. So when you take a look at the mathematical equation here, you can see the flexural strength, right, is inversely proportional to the width and the height square, but directly proportional to the applied force and the length of the beam. So I'm going to give you some of the factors, and I'm going to ask you what's this, or what's that, and what's that. You should be able to use this formula and calculate it. So here is an example. I cut it out from your question to show you how to do it. In the exam, if I choose this question, I might change the figures are in there, okay? But it's the same formula. So a ceramic beam is tested to determine its modulus of rupture. So we're asked to calculate MOR, and the question is giving you the applied force, 30,000 psi. Well, sometimes you will see these 3 as a K, a big K, same as that, okay? Talking about 1,000. And the spin length. So that's your beam length is 28, and here in this case given with inches, and the width is 2 inches and the height is 2 inches. So we will compute MOR, or modulus of rupture. If you don't remember MOR, you can write flexural strength is equal to 3 times of your force and length of that beam divided by 2 times of your width and the square of the beam height. Plug it in all the values. And when you plug it in, I'm trying to train you to write the units, as they are given. And you can also take it out as they are, So we have this value from all these values. Use a calculator and we'll come out 157 and then 500. This is a comma, not a decimal, Then PSI, right? Your force unit right there. Per mean here. So this inch and that inch is gonna be cancelled out, and you only have inch square here, unit. So inch square right there. So PSI per inch square. So those of you who are taking the final exam, make sure you show steps, show the formula, and then don't forget the unit, In all calculation, try to train yourself that way. So here is just a diagram showing you the setup for a flexible test of a ceramic beam. So here you can see the height, and here you can see the length, right? You cannot be able to see the width because they're drawing it in two-dimensional diagram. So here is your load applying, and these are your support blocks, So the force is going to go down that direction. Here is they're trying to break it into 3 parts, 3 equal parts. So you have 1/3, 3 times of it. And here is the length divided by 3 is your height, Alright, so this is another table, and it's showing you the flexural strain of materials. So the materials are that, and here is your modulus of rupture, and the unit is MPa. Alumina 380, and go all the way down 1378 for tungsten carbide. So tungsten carbide, where we use for cutting tools, the strength is the highest. If you look for the lowest strength, you can see right there, silicon nitride. Now we're going to get into another property called stiffness. Ceramics, they have the highest modulus of elasticity of all industrial materials, and they are the stiffest of all engineering materials as well. So when you take a look at the advanced ceramics, you can see they can achieve the modulus of elasticity. This is not rupture, it's a different one. 3 times greater than the steel, So even though it is clay, you can make it for elasticity greater than steel. So ceramics is really good stuff if you know how to engineer, how to engineer them. So the modulus of elasticity also can be as high as all the way to 65 million psi compared to 29 million psi for steel. So that's how much we can go about 2 times, modulus of elasticity can go, This is just showing you the internal structure, right, of a type of ceramics. You can see the crystalline structure right there. Measure of stiffness, we will use modulus of elasticity. Of course, you can use a MOE like MOR, but for modulus of elasticity, we use a different symbol. You can also write it down just like that as well. So the formula said you divide, okay, change in stress, that's your sigma, by change in strain, that's your epsilon. Temperature, right, heat, they can affect the stiffness of some ceramics. Here I'm just showing you where it went off, okay, because of the heat. Just one here also, there are many. It's just showing you a very small section of the material inside. Again, don't forget how to calculate modulus of elasticity, very simple formula. And don't forget this little triangle is telling you the change. Change is kind of like if you have like a, let's say, okay, starting point is your origin. So I'm just gonna go and give you a, let's say A, right, starting point. We can also use 1. Okay, the final point is 2. I'm just gonna write it down. Minus, that is called change. Okay, so when you read delta, you have 2 stress going on right there. Okay, and I am writing the sigma as A right here so you can see it. Just an example to show that. So if we formally write it, you have a sigma. Okay, sometimes you're going to see we're writing that with the final and the original with 0, so final minus sigma 0, okay, and then you're gonna see minus sign right there. So we're just calculating again, that's delta, okay, sigma, which is delta stress. Okay, this computer is so bad, very difficult to write. Anyway, so now you got idea how to do the strain as well. For strain, epsilon final minus epsilon initial or epsilon 0 is going to give you delta strain or delta epsilon. Okay, I'm going to go ahead and erase this for you. Then we'll get into fracture toughness. Ceramics have the lowest fracture toughness, another property. So they can get only like less than 50,750 psi. So they're therefore not materials of choice in applications where you need vibrations or impact forces, okay? Because they can crack out like that. But fracture toughness of ceramics is being improved. Again, we can improve it by adding something, so fiber reinforcement. Then we get into hardness. Ceramics are hardest of all industrial materials. That's what we use for structure, for buildings, okay, construction, we use them. And that's because of their internal structure, internal bonds that form extremely hard material, okay? And they also resist water. So ceramic makes some of the best abrasive and cutting materials. Don't forget your tungsten, yeah? Aluminum oxides, Al2O3, silicon carbide, SC, are perhaps the most popular abrasive in use today. For example, like sandpaper. So if you think about sandpaper we're using for, it is actually made of ceramics, and that ceramic type is Al2O3. Blades, cutting tools, we have already discussed about that, tungsten carbide, your WC. So here's your hardness table. You can see your material type in which you can find the ceramics, your aluminum oxide, silicon carbide here, okay, zirconia, and different types of ceramics right in there, okay. Here, I will just point it out for you, okay, 1, 2, 3. So here, you will see the hardness values right there with unit and PA. Now we're going to get into thermal conductivity. So thermal conductivity of materials refers to its ability to transfer heat And don't forget, heat is just a common word of the flow of your electron through a material. Then they usually go by filling the empty spaces, right, in their orbits. So don't forget the electron energy in the shell. So the heat is going to flow from higher temperature to lower temperature. When you think about electrons in ceramics, they will definitely resist that flow. That's why when the ceramic conduct the electricity, it's going to do it slowly. Okay? It won't go fast in it. That's because ceramic is resisting the electron flow from one location to another in the molecular structure. And why is it happening? It's because they don't have a lot of space in there. So it's kind of like a tight ion and covalent bonds in there. So if they're already bonded, you don't have much space. So you have to wait until that orbiting electron is going to free certain places in the orbit. And it's a matter of luck also. Okay, so that electron flow or the electricity happened when the electrons compete for a vacant place in the space filled with these particles. So that's it goes like little by little going. Yeah, it's because they have their original electrons and they have the current or electricity electrons coming into their molecular structure, yeah, or atomic structure, if we go one more step down. So when the shells are so full, it's very difficult to find a place in that kind of space. Okay. So that's why resistance is very high in ceramics. So therefore, we decide ceramics are poor conductors of heat and electricity. And here is the thermal conductivity of materials. Again, the same material type as in the last table, and here we have thermal conductivity, and that's the thermal conductivity unit. And again, every time you have a data set, you're going to look for the highest. Okay, train your eyes to look for the lowest. Okay, so we can scan it and see the lowest is right there. Yeah, just double check. Highest is right here, tungsten. Lowest is 0.8. Amorphous glass. So here are our familiar ceramics, and you have aluminum oxide, silicon carbide, and then your tungsten carbide. Yeah, and you can compare it to the thermal conductivity, and you can see the tungsten carbide is highest among these three ceramics. We also have other ceramics right here, like silicon nitride, and there's zirconia there. Okay, so this is just a review. So thermal expansion is the material volume is going to increase if you increase the temperature. So this is just going with the 3D. So we did it in previous lessons with length. Okay, so if you remember, so we take a look at the linear expansion, but that's just a 2-dimension. And here is we're going to look at the volume is going to definitely increase if you increase the temperature. So all materials, if you increase the heat, they're going to expand. All materials, if you decrease the heat, they're going to contract. For ceramics, okay, of all materials, they are the lowest thermal expansion. Yeah, meaning like they don't expand too much. Okay, how are we going to calculate it? So linear expansion, we go back to 2D again. So now instead of volume, we're dealing with length. It's a linear coefficient of thermal expansion. Again, thermal expansion, our symbol is your alpha, is equal to, directly proportional to the change in length. So every time you see the change, you already know you have a initial, and then you have a final, right? And then you're looking at their difference, and that's your change divided by, this is your initial length, so L0, So if you go initial with 0, you can go with 0 too. You can go with I, or you can also go with 1, yeah? And then you have change in temperature as well. So therefore you have T2, okay, minus T1 is your change of temperature. You can write whichever you want. You can also say like T0 and TF as well, it's the same thing. So change in L equal to, here we go with F in 0. Delta T, F in 0. So final lamp, initial lamp, final temperature, and initial temperature. But you can write it, okay, in any way you want. You can also go with A and B as well, yeah? Some student might even write like D and C. Doesn't really matter, just a symbol. If you know the change is a subtraction of the 2 points, that's okay. Now we have another table right there. So here in this table, we're looking at the coefficients of thermal expansion. And here we have various material. I'm pointing out, okay, what you need to pay attention in this class. So our ceramic types, aluminum, and then outside silicon, carbide, and tungsten carbide, okay. Every time we have a data set, we're going to scan, right? We're going to scan the highest and the lowest. So here we can see the highest right there. And double check. Then we're going to take a look at the lowest, which is right here, yeah? And then the corresponding material. So compared to other materials, they're kind of low, yeah? Just by looking at. So this is the same thing, the only difference is right there. We're going with a different unit of temperature. Most, in United States, we're going to use a degree Fahrenheit, okay? Other people country use degree, okay, Kelvin. And in the serious lab in the United States, we use this one, yeah? Resistivity. So ceramics, they do not readily conduct electricity, so therefore they have high resistivity to electricity, and that resistivity is again because of their structure is filled with electrons, okay, they're very tightly bound, that's why. So here's a cartoon, okay, and this cartoon is just showing you how to understand resistivity. So resistivity depends on the length. If it's too long, okay, the flow is gonna go slow. And then if it's too thick, okay, we also have issue. If it's too small, also have issues. So therefore resistivity depends on the thickness. It also depends on the temperature. If it's so hot at one point, electron flow is not gonna go, yeah? You're gonna have some roadblock right there. If it is so small, electron have an issue going through as well because the space is not limited, yeah? So formally, the electrical resistivity of material is nothing but its ability, right? Ability is something that you can do, something an object can do to resist the electron flow. And all of us, including objects, living, okay, things, non-living things, we have a major two things, okay, going on in ability. So ability to move and the ability to stay. So in other words, the potential energy and kinetic energy, okay? We either stay and locate in a position or we move with our own energy or someone else's energy, okay? Artificial energy that we make or just the space, space is born with the object, okay? Object push and pull most of the time. And if you think about the space, it's the same as what's going on in the molecular structure, what's going on in the world, the same thing everywhere in the universe, okay? Even if we have a quantum difference or we have a quantum difference or black hole difference, or we have many different kinds of explosion, whatever that is going on, we do two things, and we have two abilities. One is we can move, the other one is you want to just hang around and stay with reacting to other forces, okay, subjected to us, yeah? Another table, So we have electrical resistivity of material this time, and then I'm not going to ask you the unit, just try to pay attention to these three little ceramic types that I showed to you here. Here is silicon carbide, aluminum oxide, and cemented carbide. Okay, so here's a -8, so it's really small, 10 to the 12 here, this one 0.1, yeah? So when you take a look at it, this guy is the highest, and this guy actually higher, 10 to the power 18, yeah? So your plastic polyethylene, yeah? Okay, I am going to stop right here for part 2. Then we will get into part 3. Part 3 is just a little bit, I'm trying to keep the slides around 20, 22, 21, right? To group them together so you can be able to get it in a systematic way.